Find the average temperature on the plane x plus 5y plus z equals 7 over the square where the absolute value of x is less than or equal to 1 and the absolute value of y is less than or equal to 1, where the temperature is given by the function t of xyz is equal to the natural exponential raised to the negative z. So here we are given an explicitly defined surface. So our explicitly defined surface S is the plane, which is defined here as x plus 5y plus z is equal to 7. And I'm going to solve this for z. So this is equivalent to saying that z is equal to 7 minus x minus 5y. So here is our explicitly defined surface. And we're given a temperature function. So our function t of x, y, z is defined here as the natural exponential. And here we'll give ourselves more room. We have the function t of x, y, z is the natural exponential raised to the minus z. And so what we're going to do is take our explicitly defined function z and plug it in to this function to rewrite it in terms of just x and y. So this is the natural exponential raised to the minus z, or excuse me, minus 7 minus x minus 5y. And if we distribute that negative through, this is equivalent to the natural exponential raised to the negative 7 plus x plus 5y. And this is where we have the bounds of a rectangle, so the absolute value of x being less than or equal to 1. We, of course, know that that is equivalent to saying that x is greater than or equal to negative 1, less than or equal to positive 1, and the absolute value of y being less than or equal to 1, we, of course, know again is equivalent to saying that y is greater than or equal to negative 1, less than or equal to positive 1. So now that we have redefined our function, let's go ahead and find the parametric representation for explicitly defined surface. So we know here with an explicitly defined surface that we need to write our parameterization vector r in terms of x and y. So we're taking that explicitly defined surface that we first found and replacing the z coordinate here with it. So instead of z, we write 7 minus x minus 5y. And this is such that we know x is greater than or equal to negative 1, less than or equal to positive 1, and y is also greater than or equal to negative 1, less than or equal to positive 1. So here is our beautiful parametric representation. And we're ready to get started on finding the average temperature. So let's take a moment here and think about what exactly are we doing? How are we finding this average temperature? So to find that average temperature, we're going to need to take the surface integral. So that double integral over our surface of the temperature function, t of x, y, z, ds, and we're going to need to divide this by the surface area. So this will be the double integral over that surface S of 1 ds. So thinking about our definitions here for an explicitly defined surface, we know that this is equivalent to that double integral over that rectangular region R in the plane. And it's going to be that explicitly, or how we explicitly defined our temperature function, T, multiplied by the magnitude of the tangent, or the cross product of the tangent vectors, dA. And the surface area, since our integrand is just 1 here, this will be the double integral over that same rectangular region of the cross product of the tangent vectors in the x and y directions, dA. So we almost have everything that we need. We just simply need to go ahead now and compute the magnitude of those tangent vectors. So let's do it. We want to compute the magnitude of the cross product of the tangent vector in the x direction with the tangent vector in the y direction. So using our parametric representation above, we can see that the tangent vector in the x direction is, of course, the derivative of r with respect to x. And so this leaves us with the vector 1, 0, negative 1. And we have the tangent vector in the y direction. So that's going to be the derivative of vector r with respect to y. And this will leave us with the vector 0, 1, negative 5. So now taking the cross product of these two vectors, we are left with, we will have 0 minus a minus 1, so plus 1 I hat, minus a negative 5 minus 0 j hat, plus 1 minus 0 k hat. So this leaves us with the beautiful vector I hat plus 5j hat plus k, and we're ready to get the magnitude. So giving ourselves a little bit more room. We have the magnitude of the cross product of our two vectors in the x and y directions leaves us with the square root of 1 plus 25 plus 1. So we have the square root of 27, which of course we can simplify. We know that 3 times 9 equals 27, where 9 is a perfect square. So this leaves us with 3 times the square root of 3. And so using this magnitude here, we are officially ready to start computing the surface integral and the surface area using a surface integral. So let's go ahead and let's compute the surface integral first. So we want to calculate the double integral over this two-dimensional region R of the temperature function T of x, y, z multiplied by the magnitude of the cross product of the tangent vectors in the x and y directions, dA. So plugging in what we know, we have the double integral from negative 1 to 1, the integral from negative 1 to 1 of our temperature function, the natural exponential, raised to the negative 7 plus x plus 5y, multiplied by that magnitude. So that's 3 times the square root of 3. And since our bounds are constant here, you can use whichever order you prefer. So we'll do dx dy here. All right, so evaluating that inner integral, I have the integral from negative 1 to 1. And actually, we can go right ahead here and put that 3 times the square root of 3 on the outside. And that's the natural exponential raised to the negative 7 plus 5y plus x dx, which simply integrates to 3 times the square root of 3 times the natural exponential raised to that negative 7 plus 5y plus x. And it's technically divided by 1, but we don't even need to write that. And that's from negative 1 to positive 1. So evaluating, we have 3 times the square root of 3 multiplied by the natural exponential raised to the negative 7. And you know what? Let's separate this out here. Let's think of this as 3 times the square root of 3 multiplied by the natural exponential raised to the negative 7 plus 5y. And now I've separated out the natural exponential for the x using properties of exponents. So that's the natural exponential raised to the 1 minus the natural exponential raised to the negative 1. And oops, we did it. That's all we need. All right, so now that we have, again, this was the inner integral, we're going to use this integral here to find the outer integral. So our outer integral, I'm going to pull all the constants to the outside of this integral. So that means that we have 3 times the square root of 3 multiplied by the natural exponential minus the natural exponential raised to the negative 1 times the integral from negative 1 to positive 1 of the natural exponential raised to the negative 7 plus 5y dy. We could have even factored that natural exponential raised to the negative 7 out as well. But leaving this as it is, we can integrate this, and this is going to leave us with 3 times the square root of 3 times the natural exponential minus the natural exponential raised to the negative 1 multiplied by the antiderivative, which is the natural exponential raised to the negative 7 plus 5y divided by 5. And we're now evaluating from negative 1 to 1. And we'll give ourselves a little more room. And so we have 3 times the square root of 3 times the natural exponential minus the natural exponential raised to the negative 1. And that's all divided by 5. And this is now multiplied by the natural exponential raised to the negative 7 plus 5 minus the natural exponential raised to the negative 7 minus 5. And simplifying, we are left with 3 times the square root of 3 multiplied by the natural exponential minus the natural exponential raised to the negative 1, all divided by 5. And this is now multiplied by the natural exponential raised to the negative 2 minus the natural exponential raised to the negative 12. And all of these are constants. You could, of course, just apply the FOIL method here and distribute these out, but there's nothing wrong with this answer. It's not particularly beautiful, but it will work just as well. So here we go. That is the surface integral for our explicitly defined function, temperature function. So now we need to find the surface area. So that's going to be that double integral over our rectangular region R of 1 multiplied by the magnitude of the tangent vectors or the cross product of the tangent vectors in the x and y directions, dA. So this leaves us with the double integral from negative 1 to 1, the integral from negative 1 to 1 of 3 times the square root of 3, and the order doesn't matter here, dy dx. Pick your favorite. And I'm actually going to separate this out since we have only constant bounds here. I'm going to separate this out to the product of two double integrals, or two single integrals, excuse me. So I have 3 times the square root of 3 multiplied by the integral from negative 1 to 1 dy multiplied by the integral from negative 1 to 1 dx. And so in evaluating these, we are going to be left with 3 times the square root of 3. And the y integral is going to leave us with 1 minus a minus 1, so 2. Same thing with that x integral, you're left with 2. And if you're not seeing where these came from, don't skip the steps. Show the workout. Right, so real quick. If you saw it, continue going. See if you get the same answer as me. If not, follow along. So let's say I take this integral with respect to x, and if we integrate this, I get x from negative 1 to positive 1, which will be 1 minus a minus 1, which leaves us with 2. And we get that same exact answer for the y integral. So the surface area here is going to be, we have 4 times 3, so we have 12 times the square root of 3 square units. Now don't get so excited that you found both integrals that you forget we need the average temperature. So the pièce de résistance, our average temperature, we have everything we need. We can plug this right in. We have the double integral over the surface of our temperature function, T of x, y, z, ds. And this is divided by, need a little bit more room, divided by that surface area, surface integral. ds. And so we found the temperature is 3 times the square root of 3, all divided by 5, multiplied by the natural exponential minus the natural exponential raised to the negative 1, multiplied by the natural exponential raised to the negative 2, minus the natural exponential raised to the negative 12. And that is all divided by 12 times the square root of 3. And so we've got nice cancellation here. Those square roots of 3's cancel each other right out. We, of course, know that 3 goes into 12 4 times. And we are left with a beautiful final answer here. We have the natural exponential minus the natural exponential raised to the negative 1. Actually, we'll move this over so we have plenty of room. This is in the numerator. Natural exponential minus the natural exponential raised to the negative 1 multiplied by the natural exponential raised to the negative 2 minus the natural exponential raised to the negative 12. And that's all divided by 5 times 4, which is 20. And so this is our beautiful final answer. And now I want you to note, depending on how you approached the integration of the natural exponential, your answer might look different than mine. And that's okay. There's different forms of the correct answer here. So a good way to check, let's note, if we were to FOIL out that numerator, the natural exponential minus the natural exponential raised to the negative 1 times the natural exponential raised to the negative 2 minus the natural exponential raised to the negative 12. If you FOIL this out, again, there's a lot of properties of exponents here, but we are algebra pros by now. So, or practice makes perfect. So if we FOIL this out, we have the natural exponential times the natural exponential raised to the negative 2, which leaves us with the natural exponential raised to the negative 1. I have the natural exponential multiplied by a negative natural exponential raised to the negative 12. So 1 minus 12 leaves us with the natural exponential raised to the negative 11. Next, we have minus the natural exponential raised to the negative 1 times the natural exponential raised to the negative 2. So that's minus the natural exponential to the negative 1 minus 1, which is minus 3. And last but not least, we have minus the natural exponential raised to the negative 1 minus the natural exponential raised to the negative 12. So negative times a negative gives us plus that natural exponential raised to the negative 1 minus 12, which is minus 13. So that's equivalent to our numerator. So this would be a great way to check to make sure, does your answer match my answer?